In the last video, we showed you the Cauchy-Schwarz inequality. Cauchy-Schwarz inequality. And I think it's worth rewriting because this is something that's going to show up a lot. It's a very useful tool. And that just told us if I have two vectors, x and y, they're both members of Rn, and they're both non-zero vectors. And that was an assumption we had to make when we did the proof. Otherwise, there was a potential of dividing by one of their magnitudes. So that would have been a big no-no. But if we assume that they're both non-zero, then we can say that the absolute value of their dot products is going to be less than or equal to the products of their individual lengths. So that's the length of vector x, and we defined that a couple of videos ago. And then this is the length of vector y. And of course, this is just a regular number, and then each of these are just regular numbers. They're not vectors once you take a length. The length of a 50-dimensional vector could just be the number 3. It's just a scalar value. So this is just scalar multiplication here. And we also learned that the only time that this inequality turns into an equality is the situation where x is equal to some scalar multiple of y. And so in some textbooks, you'll say, and this has to be a non-zero scalar multiple. But that's a bit obvious. I told you that x and y are non-zero. So if this was 0, then x would be 0. And I just said that x is non-zero. But if you want to say there, you could say that c also is going to be non-zero. But that essentially just falls out of this information there. But if this is the case, and if and only if this is the case, then we can say that the absolute value of the dot product of the two vectors is equal to the product of their lengths. Now, this is all just a review of what I did in the last video. Now, what else can we do that's useful with it? So let's just play around a little bit. But, well, I can't claim to be experimenting. I know where this is going to go. Let's see what happens if I were to take the length of x plus y. So I'm going to add the two vectors and then take the length of that vector squared. Well, we know from a couple of videos ago that the length squared can also be rewritten as the dot product of a vector with itself. This right here, x plus y, I know it looks like two vectors, but it's two vectors added to each other. So it's really a vector. X plus y is a real vector. I could graph x plus y. So the length of x plus y squared, I can rewrite it as the dot product of that vector with itself. So x plus y dot x plus y. And all of these are vectors. These aren't just numbers. And this is the dot product. It's just not normal multiplication. But we saw 2 videos ago that the dot product has the distributive and the associative and the commutative properties just like regular scalar multiplication. So you can kind of FOIL this out if that's how you remember multiplying your binomials. Or I always think of it more as just doing the distributive property twice. So this can be rewritten as x dot x. Actually, let me write it as a distributive property, because that's sometimes not obvious to a lot of people. So let me write this x as a yellow x, and let me write this whole term as x plus y. So this right here can be rewritten as x dot, so this x dot, this x plus y, and then it would be plus this y dot, I wanted to switch colors, plus this y dot x plus y. It's good to see that when you're multiplying these, you're just applying the distributive property, right? All I did is I distributed this term along each of these terms in this sum right here. So then I got this. And then I can distribute each of these into the sum. So then this becomes, I'll be careful with the colors, x dot x plus x dot y. Maybe this was a little bit overkill, but I think it's good to see that this isn't just some magic here. And we're just using the exact properties that we proved of the dot product. So that's that right there. And then it's plus y dot x. So y dot x plus this yellow y dot the yellow x, dot the yellow, sorry, dot the blue y, dot the blue y. So the magnitude or the length of our vector x plus y squared can be rewritten like this. And this, and I'll just switch back to one color. So this equals that. And all of that